implicit differentiation. But before we go into this implicit differentiation, I would like to make a little bit of a review for basic differentiation. Let's say if we want to differentiate x, so we will get 1. But if we want to differentiate y with respect to x, so we'll have dy dx. What about if we want to differentiate x squared with respect to x? So we'll have 2x, and then we have to differentiate again the function inside, which is x. So we'll have 2x. But if we want to differentiate y squared with respect to x, so we'll have 2y, and then we have to differentiate the function, which is y, respect to x. So we will get 2y dy dx. Compared with differentiate x squared, we have 2x. And one more, if we differentiate exponential function of e to the power of 2x, so we'll have e to the power of 2x, and then we have to differentiate 2x. So we'll have e to the power of 2x. So since 2 here is a constant, so I write down 2. And if we differentiate x with respect to x, we'll have 1. Or we can write down as 2e to x. But if we want to differentiate e to the power of 2y with respect to x, so we'll get e to y, and then we have to differentiate the function, which is 2y. Now since 2 is a constant, so I write it down at the front. And if we differentiate y with respect to x, so we'll have dy dx. Or we can write down as 2e to y dy dx. So from these 3 examples I've shown here, as you can see, if we differentiate x, we'll get 1. But if we differentiate y with respect to x, we'll have dy dx. If we differentiate x squared with respect to x, we'll have 2x. But if we differentiate y squared with respect to x, we'll have 2y dy dx. So the difference here is we have dy dx at the back. We have to multiply with dy dx. Now let's look at 4 examples of implicit differentiation. Let's say we have yx equals to x squared, and we want to find dy dx. So the first step is, since we want to find dy dx, so we have to differentiate both sides with dx. Okay, and then we have to differentiate both sides with respect to x. Now since we have y multiplied by x, so we have 2 functions here, so we have to apply the product rule. So from the product rule, y is our u and x is our v. So from the product rule, and the formula we'll have is vu prime plus uv prime. So now our v is x and u prime, so if we differentiate y, so we have dy dx plus u, which is y, multiplied by v prime, so differentiate x, equals to, and if we differentiate x squared with respect to x, we have 2x. Now we simplify on the left hand side, so x dy dx is equals to y, and this, when we differentiate x with respect to x, we have 1. Oops, sorry, this should be plus, is equals to 2x. And we rearrange, see, we want to find dy dx, so dy dx is equals to 2x minus y over x. So this is our solution for yx equals to x squared. We are solving this by using implicit differentiation. Let's take a look for another example. So we have y squared plus 2 equals to 2xy. And again, we want to find dy dx. So the first step, we have to put d dx at the front for both sides. And then now let's differentiate. So if we differentiate y squared with respect to x, so we'll have 2y dy dx. And if we differentiate 2 with respect to x, we have 0 equals to, and if we differentiate 2xy with respect to x, we'll have 2, since 2 is a constant. Again, we have to apply the product rule, which is v u prime, which is 1, plus u v prime. Then we have 2y dy dx is equals to 2y plus 2x dy dx. And we can factorize and simplify this. We have dy dx, 2y dy dx minus 2x dy dx equals to 2y. And then we have to factorize our dy dx. So we have 2y minus 2x equals to 2y. So dy dx equals to 2y over 2y minus 2x, or we can factorize 2y minus x. So we have y over y minus x. Next, we have tangent xy equals to x cubed plus 5x. So we want to find dy dx. As usual, we have to differentiate both sides with respect to x. So d dx for tangent xy and d dx for x cubed plus 5x. So if we differentiate tangent, we'll have secant squared with the same angle, but we have to differentiate the inner function here. So d dx xy equals to, on the right hand side, we have 3x squared plus 5. So secant squared xy, again, if we differentiate xy, we can use the product rule. So we'll have x dy dx plus y multiplied by 1 equals to 3x squared plus 5. Again, we have to rearrange since we want to find dy dx. So x dy dx plus y equals to 3x squared plus 5 divided by secant squared xy, and dy dx is equal to 3x squared plus 5 over secant squared xy minus y, and divide everything with x, or you can write it down as over x over x. Also, if you want to simplify this, so we'll have 3x squared plus 5, and we can multiply with secant squared here, secant squared. So we'll have minus y secant squared xy divided by x secant squared xy. Next example, so we have ln y plus e to the x equals to x over y. Again, we want to find dy dx, so differentiate both sides with respect to x. Now, if we differentiate ln y with respect to x and differentiate e to the x respect to x, and on the right hand side, since this is a rational function, so we'll have to use quotient rule. So for the quotient rule, and the formula is, if we differentiate quotient rule, we'll have v u prime minus u v prime over v squared. So we'll have y differentiate x equals to 1 minus u v prime, which is differentiate y respect to x, over v squared, which is y squared. Now, let's look at on the left hand side. If we differentiate ln y with respect to x, so we'll have 1 over y, and then we have to differentiate the function inside, which is y, so we have dy dx, plus differentiate exponential function, we have e to the x, equals to, so if we can simplify this, we have 1 over y minus x over y squared dy dx. And then we have to rearrange, since we want to find dy dx here and here, so we can factorize 1 over y plus x over y squared dy dx equals to 1 over y minus e to the x. Therefore, dy dx equals to 1 over y minus e to the x over 1 over y plus x over y squared. Now we have to make something with this. So let's look at the numerator first. For the numerator, this is over 1. Then we have to cross multiply. So we'll have 1 minus y e power of x over y and divide by again. So since we have y squared and y, so this one have to multiply with y. So we have y plus x over y squared. And then we can write down as 1 minus y e to the x multiplied by y squared over y multiplied by y plus x. So we can cancel out this y and y. So we'll have 1 minus y e to the x y over y plus x. Now let's look at one more example. So we have 3 e to the power of 5s plus 1 equals to sin s plus t. Now we want to find ds dt, means that we want to differentiate with respect to t. So we have to put d dt for both sides. If we differentiate 3e 5s plus 1 and sin s plus t. So don't forget the bracket here. So if we differentiate s function with respect to t, so we'll have ds dt at the back. So 3e 5s plus 1, and then we have to differentiate d dt 5s plus 1 is equals to, when we differentiate sine, we have cos s ds dt plus 1. Since we differentiate t respect to t, so we'll have 1. Now let's 3e 5s plus 1, and we differentiate 5s respect to t, so we'll have 5 ds dt. And if we differentiate 1 respect to t, we have 0 equals to cos s ds dt plus 1. So again, we have to rearrange this. So we'll have 3 times 5, 15 e 5s plus 1 ds dt minus cos s ds dt equals to 1. So if we factorize ds dt, so we'll have 1 divided by 15 e 5s plus 1 minus cos s.